So everything is a signal, and all of these complicated looking shapes of signals can be decomposed into pretty shapes like what we have on the right. Okay. That's the goal of signal analysis. We're trying to decompose a signal and think about them purely as frequencies. And these shapes, these sine waves, we can think about at their frequency range. So we have some signals that are low frequency, some signals that are high frequency, and so on. So the really important part is that real signals can be represented as a sum of all these sine signals. That's the whole principle of Fourier analysis, and is a really, really important principle in math. The details of it aren't actually that complicated. It's worth watching some YouTube videos on if you care. But just as a demo that I made, a little small thing I put together to show you what this looks like. So on the left, I'm going to draw a waveform, okay? I'm going to draw something that looks kind of complicated, okay? And so that white line represents the average value of the signal. That's the DC zero frequency, right? So DC is a zero frequency wave. Does that make sense what I'm saying? That DC is zero frequency? Does that make conceptual sense to say it like that?
Yeah.
Okay. Feel free to stop me if I'm talking. There's ever any confusion, by the way, and I don't stop to ask questions. Please stop me. So if I click play here, you'll see we add in one order term, it starts to look like a sine wave. We add in a second term, now it's the sum of this wave, n equals 1, and the second wave, n equals 2. You keep adding in more waves at different frequencies. Again, notice how all these waves on the right just have one frequency in them. But by adding them all together, you can create the shape of the original signal. Okay? Does that make sense? Does it seem that maybe it's the math is really kind of abstract? Yeah, questions? Ben?
Wait, so like, um,
I was gonna ask like, is it like adding like simpler sine waves together until it gets like the closer to the actual wave?
It's exactly like that. And it might be
Okay.
easier to see if I do this in Desmos as well. If I just like graph sine of x and then so if I graph sine of x, it looks like that. If I add in sine of 2x, it starts to look more complicated. Maybe like a 0.3 cosine of 4x plus 5. And you can see if I keep adding in waves of different frequencies, each one of these individually is a clean looking shape, right? But if I keep adding them together, I eventually get a complicated shape. And the goal is to get that complicated shape to reproduce our actual signal. So yeah, Omar.
Does this have anything to do with DC transients in circuits like that, or no, not really?
DC trends. So a lot of the time in AC circuit analysis, you'll split the actual response of a circuit into the transient and the steady state response. So what that means is if we go to like what that means is you give some input to the circuit. Maybe it's like a battery that you turn on for 5 seconds and then turn off and see what happens. Usually your output of the circuit looks something like let's do like 550 times that. Okay. And then plus sine of 2x. So this might be what your circuit looks like. So looking from time equals 0, your output initially looks really ugly and messy, right? This is not a simple shape that we have initially. But then as we progress to a long time outwards, now it starts to look really simple and clean. So this period right here, this is what we call the transient, where things are ugly and it's not exactly clear what's going on. It's still a sum of sine waves, but it's a complicated function. It's not easy to think about. Whereas out here, it becomes simple and it's just a sine wave. So that's transient versus steady state. Yeah, Arya?
Is it because like the factor of the e to the 2x part like decreases with
Exactly.
like
This is a
out?
decay and it decays out. Yeah. Ishan?
so like for the Fourier transform, does it just like like add the sine waves and like for each one, like do we need to like plug it in individually to like the AC circuit when we're doing like the equalizer? Or do we just like do they go in all at once and do like the different like capacitors like they filter out the frequencies?
So it's the second one, and so you're getting exactly to my next point. So before we get there, are there any questions about this right here? The fact that we can represent a complicated signal as a bunch of simple sine waves. Yeah, Ben?
Oh, what are like the n equals? Like, what do those mean?
those are the orders of the Fourier analysis. So it comes down to math. Basically, it's the frequency. Higher n means higher frequency.
Oh, okay.
Um, it's a little different than that, but that's what I'm modeling it as, basically. By the way, this is just HTML. I'll send these out. These are things that you can run on your own web browser. That you can just play with it yourself. But it's fun because you can just like draw something and then see how does the Fourier series assemble to look like it. And for any shape you draw, you'll be able to get a series that looks close to that shape after it adds enough terms in. So even this shape, which is super strange, after we add enough terms, we're still getting close to that shape. So yeah, that's the Fourier series. Are we all good on that? The moral is that any complicated signal is representable as a sum of sine waves of single frequencies. And single frequencies are easy to analyze. Okay. So now going back to this. Let's go back to DC circuit theory and think about superposition. If I give you a circuit like what we have on the left, where we have three sources that are hard to think about, and like how do you even start analyzing the circuit? You can use nodal, but then you get a bunch of equations and it gets really ugly. Well, it's going to be easier to split this circuit by first ignoring two of the sources and analyze it one source at a time. Say when we do that, we find this resistor drops 3 volts. Okay. Then say we analyze this circuit on the right over here, and we see that the resistor drops 2 volts there. Then we analyze this circuit down here, we see the resistor drops 5 volts here. That means, and this is a fact, this is the law of superposition in circuits, when I have all 3 of these batteries in the circuit together, this resistor will drop 10 volts. It's just the actual sum of the response to each of the individual sources. This is a really important concept in circuit analysis, especially the linear circuit analysis that we're doing. The fact that sources are superposable. And it's what lets us analyze things with Fourier series. If you recall, what we just talked about in this demo here, was that I can represent my complicated input wave as a sum of a bunch of simple inputs. And what I showed you here was that if you have a bunch of different inputs, you can just think about each input one at a time. You don't need to think about all of them together. So instead of thinking about this really complicated shape that we have here, we just think about how the circuit will respond to the simple shapes that have a single well-defined frequency and analyze it one at a time. So does that make sense, the goal there? Any questions on that?
Oh yeah, just like to add, like superposition also is like the ability to add things like, you know, the charges in superposition. It's like pretty much the same thing, but like you
Yeah, you
add
can use
the forces.
superposition for logic fields.
Yeah, it's a general physical
Yeah.
idea that if I have one thing and I put another thing in, the response is the same as just the sum of those two things individually. It's a
Yeah.
very general idea of linearity. That's the definition of linearity, I guess. If you've ever, at some point in your life, you'll take linear algebra and you'll learn that that is the definition of linearity, and it's like a defining property that lets us do math. It's an important thing. Yeah, Arya?
So for superposition theorem, if there's a current source, then it's replaced by an open wire, right? Like,
Yeah, I mean that's a detail of how to like do the actual algebra and solve it out, but that's true. That's correct because a current source forces a particular current to be applying, but it doesn't care about what voltage is around it. So an open wire can have any voltage between those wire nodes, but it can't have any current, and that's what. But that's kind of beyond the scope of what we're talking about today. We're just thinking about voltage source for now. So, big moral. When thinking about AC circuits, we only need to think about what the circuit does to a wave of particular frequency. If we know what the circuit does to like sine of x and sine of 5x, sine of 100x, sine of 3000x, then we know what it'll do to really complicated shapes like this as well, and actual real audio signals like this. And so then we can think about how to get to an actual equalizer. Okay, so that's where we're at. Now, to actually implement this, we need things that are frequency dependent. If I just have voltages and resistors, there is no frequency dependence in that circuit. I won't do anything interesting. Capacitors are the simplest way to get some sort of frequency dependence. So just as a review of what capacitors do, recall that the way capacitors work is that we put some voltage between two plates, and due to that voltage, you have charges that migrate to separate between the plates. Okay. Now I have a question for you. If we have a bunch of positive charges up here and a bunch of negative charges up here, why is that a voltage? Why does that create a voltage?
Because like the
create
positive
a
charges and
potential
negative
difference.
charges, the electric field, yeah, from high potential to low potential, and then they create a voltage across the capacitor.
And
Yeah, so that's one reason. Someone else had something.
I think because voltage is potential difference, that too.
So
Also, it creates
if we're
an
thinking of,
sorry.
go ahead. I don't know who that was. Sorry.
Also creates an opportunity for, say, the positive charges to flow through the negative charges.
Okay.
So it
What-
also creates opportunity for flow.
Wait, I'm
Yeah.
pretty sure it's just like the positive charges and the negative charges from the top and bottom. They create an electric field, and where there's an electric field with charges, there's always electric potential
Yeah, Ishan, you had
difference.
something? Was that Ishan that said that?
Yeah.
Oh, bro, I can't tell. My bad. Okay, so yeah, you're all saying correct things in different ways. So you're all right. What I was going for was basically because there's positive charges built up here. If I put a positive charge right here, it's going to be repelled from here and attracted to here at the bottom. Sorry, it's going to be repelled from the top plate and attracted to the bottom plate. Remember that we think about potential like a ball on a hill, right? If I have a ball right here, that ball has big potential. It'll roll down the hill and lose that potential. A positive charge sitting on this top plate is exactly like that. It has a high potential because it wants to get away from those positive charges and move towards the negative charges. Once it reaches the negative charges, it's lost that potential. It's rolled down the hill. Okay? So that's why building up those charges builds up potential. And that's the exact same thing as saying it builds up a voltage. Perhaps you've seen this equation on the left for C equals Q over V. That's just the defining equation for a capacitor. That's how we define capacitance. It's the amount of charge, or sorry, amount of charge per unit voltage. So if it takes 5 coulombs to build up 1 volt, then we have a 5 farad capacitor. Whereas if it takes 1 coulomb to build up 1 volt, then we have a 1 farad capacitor. That's just the units. So are we clear on just the basics of what a capacitor is? What is frequency dependence? We'll get to that. Basically, it's saying if I have sine of x versus sine of 1000x, the circuit will do different things. But we'll get to that. Okay, so the defining property of a capacitor, there's a differential equation that you can look at. We're not going to do that because calculus is not a prerequisite for this class. But the defining property physically is that voltage cannot instantaneously change on a capacitor. Can someone tell me why that makes sense? Why does it make sense that voltage cannot change instantly on a capacitor based on what we just talked about? Yeah, Ishan?
Because if there's a voltage buildup and the chart, it takes time for the charges to move back. Like whenever there's a voltage and then the voltage dissipates, it takes time for the charges to go back to steady state.
Exactly. Arya, did you have something in addition to that?
Yeah, so like if all the positive charges move that way, then they won't really be attracted anymore because there's positive charges there anyways. So
That's a good point too. Yeah. But so yeah, it's exactly what you guys said. Because the charges can't just teleport, right? Oh, I wrote it there, bruh. Okay. Because the charges can't teleport, the voltage can't change its state. I didn't mean to write it there. I realized this question was completely silly. You guys are just reading the slide. Okay. Well, you get the point, right? Is there any confusion about that claim that charges cannot teleport instantly, so we can't change voltage instantly? The separation of the charges is what causes the voltage, right? So if that can't change instantly, then the voltage can't change instantly. Current can change instantly. The moment I turn on this battery, immediately charges can start flowing. Oopsies. If I just turn on the battery, immediately charges can start flowing, and that's fine. But the voltage can't drop from 5 volts to negative 5 volts instantly. It can only start smoothly changing. So, okay. Now, in an RC circuit, you have a resistor and a capacitor with a battery. So I'm going to show this in LT Spice actually. So let's go to LT Spice. We're sort of running out of time, but maybe we can do the design thing next time. That's okay. I'm going to put a battery down. I'm going to put a wire, capacitor.
Oh, we can't see the LT Spice.
Thank you. So I'll just start again. Okay. So I'm going to put a battery down. I'm gonna put a resistor, a capacitor, a wire. And then ground. Okay. Then I'm gonna go to this battery, right click on it, and press advanced. Okay. And then I'm gonna make it a pulse. So I'm gonna have the initial voltage be 0, the on voltage be 5. So it's gonna be a pulse that goes from 0 volts to 5 volts. It has no delay, so it immediately turns on. It takes a very short amount of time to turn on, a very short amount of time to turn off, and it stays on for 5 seconds. And we do it for 1 cycle. Okay. Maybe 30, we'll say. Okay. So what this voltage looks like, if I make a plot of voltage the input voltage over time, we're saying it's on for 5 seconds and then it's off for the rest of time. So right here is 5 seconds. Okay, so we have 5 volts for 5 seconds and then we turn the battery off and we're seeing what happens. So now I'm going to run a time domain simulation. So you're going to go into .ac, click transient, and then we'll set the stop time to 30 seconds. Actually, we'll do 20 seconds. And we'll just press OK. That's all we need to set. Also, make sure to set values for your components. I'll just do 1 and 1. Okay, so can someone tell me what they expect to see here? When I plot the voltage of the capacitor, what do we expect to see? Yeah, Ishan?
So initially it'll be going and approaching 5, but then it'll probably like cut short of 5, like, cause if I did the calculation, it would either go almost to 5, but it wouldn't reach 5, and then it would start going back down after 5. It would go down in an exponential curve.
Right, exactly.
Like,
so
yeah.
I'm gonna first plot the oopsies. Okay, so this is a plot of the battery voltage. The blue curve is the battery voltage. So you can see the blue curve is at 5 volts for 5 seconds, and then it drops down to 0. Now this curve, the green curve, is the capacitor voltage. It goes from 0 to 5 volts, almost all the way up, but it doesn't quite reach, and it goes smoothly because the voltage on the capacitor cannot change instantly, and then it smoothly drops down. What about the current? When I plot the current through the capacitor, what's that gonna look like?
A spike.
It'll quickly go up and then and also quickly go down.
No, it would still be smooth. It would still be like smooth, kind of.
So it does quickly go up. It instantly changes.
And then slowly goes down. Yeah, slowly.
So notice the current axis here is on the right. So initially it's 0 amps, then it snaps up to 5 amps. But then it slowly decreases back down to 0 amps. Then the moment we turn the battery off, it snaps down to -5 amps, but then it slowly goes back to 0 amps. So here, the current can indeed change instantly. The voltage cannot change instantly. That's the moral here. Are we good on that?
Yeah.
Yeah.
Good.
Cool. So, okay, let's go back to this. So I have another simulation here, but maybe I'll show this is basically the same thing, but it shows a little more visually. So this is a DC circuit. You can see I turn the battery on, we build up a potential difference across the plates, and that potential difference shows the voltage in the battery. Then I turn the battery off and we lose the potential in the battery as current flows, right? So as we build up a voltage, we're trying to match V in, we turn it off, we're no longer matching V in. And you can apply KVL and think about, is the resistor dropping voltage here, is it not, and so on. So RC circuits are filters. And this is really the essential point of today's lecture. An RC circuit is itself a filter because of the fact that a capacitor takes time to respond to a change in voltage, okay? So when we're just thinking about filters in general, we use this terminology of low pass, mid pass, and high pass. What this is saying is if I make a plot of how much signal gets through as a function of frequency, right? Then a low pass filter lets all the signal through initially. A low pass filter lets all the signal through at low frequency, but blocks high frequency. Okay, I'll do that. A low pass filter lets through low frequency and blocks high frequency. Hence the name, it passes low frequency. A high pass filter passes high frequency and it blocks low frequency. You might also hear this terminology of band pass frequency. So a band pass filter allows a band of frequency and stops stuff outside the band. And a notch filter is a band stop filter. So it blocks frequencies in the middle range and it allows frequencies outside of that middle range. That's just the vocab terms when talking about filters that I'm going to use. So different filters, in particular RC filters, but that we're going to talk about, but filters in general, are parameterized by a cutoff frequency. That's right here. For bandpass filters, you need 2, but for these high pass and low pass, you need 1. And that tells you when the curve essentially reaches like 50% or some other definition of its initial size. So that happens right here, it's in decibels, and right here. So a lower cutoff frequency for this, what kind of filter is this one right here? That on the top left corner.
Low pass.
Low pass.
Low pass, right? And so if I have a lower low pass filter, it's gonna look like that, right?
So like if the lower the steeper the curve, or like the
Not
how
steeper.
high?
Lower meaning lower cutoff frequency. So that just it's like
Oh,
it's a horizontal shift. Steeper relates to the order of the filter, and we'll talk about that. Okay. So before we go to the simulation of the filter, which I think will be quite informative, think about KVL for this circuit. So say the capacitor has a ton of voltage dropped across it, and the battery is supplying a big amount of voltage. How much voltage does the resistor drop?
Almost none.
Almost nothing. Exactly, because
Yeah.
of KVL. The voltages around the loop sum up to 0. Okay. So what about when the capacitor, and I won't ask, I'll just say it. When the capacitor is dropping basically no voltage, the resistor is dropping the rest of the voltage.
Yeah.
So if our input signal is this battery, and our output signal is the voltage that we measure, like right here, we connect our voltmeter, and we just measure across the capacitor, then our signal is basically how much voltage is the resistor not dropping, how much voltage is the capacitor dropping. And we should see that for really high frequencies, this voltage has some relationship to this voltage. For really low frequencies, it'll have a different relationship. So with that in mind, let's go to the simulation. So right now we have a frequency at the input. So the blue dots are like the positive charges moving through the circuit. The red arrow and like how bright the resistor is represents how much voltage the resistor is dropping. And you can see like the voltage lines in the capacitor. So notice how high the battery voltage gets. That's V in, that's constant. That's going to get the same amount of height every time. Whereas, and the capacitor voltage is not quite reaching as high as it goes. So the battery voltage maybe gets up there, that high, but the capacitor voltage only gets up here, okay? So we would say this circuit has a gain of about, maybe the height of that 7 and the height of this is 10. The circuit has a gain of about 0.7. 70% of the input signal gets through to the output right here, okay? So if I increase the frequency, if I move this knob at the bottom left up, will we expect that to decrease or increase? Will more get through or will less get through?
Decrease.
More get through.
Less.
Less decrease.
Less.
So Ishan said decrease. Why do you think decrease?
Because it decreases because the capacitor, like, it can only like change charge, like it can only go from like 0 voltage to like the max voltage so fast. It's dependent on its like capacitance. But then when the frequency increases, the time that the capacitor takes to like go up to max voltage, by that time the voltage would already be like negative. Like if it was positive and the capacitor is trying to go to the max positive voltage, by the time it even goes like a little bit of the distance, it'll already be negative, like the source voltage. So then in the end, like the capacitor will have almost no voltage across it.
Yeah. So someone else had an argument for it'll increase. Did anyone want to give their argument for that case? You might not be wrong. You can give your argument. Okay, that's fine. So Ishan is right. As I increase the frequency, if I make it a lot faster, you can see, I'll draw it in green. The battery signal still gets as high. It's still going all the way up there, but the capacitor signal is maybe only down here. So maybe that's like 0.3 at the high frequency. And if I increase the frequency even more, like as fast as I can in this simulation, you can see the capacitor voltage can only change so fast. And so I want the voltage to change really, really quick, but the capacitor is just too slow. It can't react fast enough. And so it's stuck on really tiny changes. Whereas if I go down to really slow frequency, like all the way down here, you can see the capacitor voltage is able to follow the battery voltage pretty effectively, and it can reach that. So is this a high pass filter or a low pass filter?
Low.
Low
Low
pass.
pass.
Exactly. The low frequencies are going to get through, the high frequencies are not. Are there any questions on that so far?
Wait, is low pass just basically a resistor and a capacitor, or like?
So in this schematic, yeah, you can have a low pass or high pass filter is just a resistor and a capacitor. But you ask a good question. So this configuration is a low pass filter. What if I measure the voltage across the resistor instead? Would I have a low pass or a high pass filter?
High pass.
Yes,
Yeah, high
exactly.
pass. Because it would,
And why?
because more voltage or current would be running through the resistor at more times.
That's part of it, but maybe from like KVL,
Yeah.
can you justify it?
Yeah.
Or maybe someone else? Does someone else
Or
wanna...
more of the voltage across the resistor.
Wait, can you repeat the question?
So we saw that at low frequencies, the capacitor is able to drop a large amount of voltage compared to the battery. At high frequencies, the capacitor cannot drop a lot of voltage. At high frequencies, the capacitor struggles to drop most of the voltage, right? Remember that the amplitude here was really tiny. So the question is, if I were to measure across the voltage on the resistor instead of the voltage on the capacitor, would I see a high pass filter or a low pass filter if that was my output? Like if I connected my voltmeter prongs right here,
Yeah, you'd see a high pass.
you'd see a high pass. And I
Yeah.
want someone to give me a justification for that through KVL. Yeah, Arya?
So because less voltage is passing through the capacitor since
Yeah,
it's
more voltage.
Go ahead, Arya.
So it's basically like the inverse of like
Yeah,
if it's
there
like
would be-
Yeah, since
low
less voltage is across the capacitor, that means more voltage
More, yeah.
has to be across the resistor
Yeah.
because
Because of
because of
KVL.
KVL, since it's a single loop, that means the voltage across the two components, resistor and capacitor, has to equal the voltage across the battery or supply.
Yeah, you're right. I think just in the future, if someone's answering a question, don't interrupt them. I think Arya was gonna give an answer. Sorry about that. But just yeah, but you guys are right. Because the capacitor can't drop the voltage, the resistor has to, and then vice versa for the other frequency range. So this is the simplest version of a filter that we can get. It's an RC filter. You can do the same thing with an RL circuit with an inductor. We're not going to talk about that today, but that's fine. And so that gives you a filter. At high frequencies, a lot gets through. At low frequencies, not a lot gets through. Okay. And you can see, we talked earlier about the time constant. So if I bump up, maybe Arya, you want to answer this one. If I bump up C and I bump up R, what am I doing to the time constant of the circuit? Or what am I
So
doing to, like,
increasing it.
RC. So
Yeah, it
you're
increases because the time constant is RC. T equals RC.
Or R times C. Or it's proportional to resistance and capacitance.
yeah, so the time constant increases. So what about like just the reaction speed? Is the capacitor gonna be slower to react or faster?
It's going to be
react?
slower to react
lower, so yeah, slower react.
It's gonna be slower to react.
because
so-
it would
Because it's less time.
Even
Less
longer-
time
need,
to
need
time
more
to
time
charge
to build up
voltage.
the full charge. Or it needs
Exactly.
more time to charge.
Yeah, so even at this slow frequency, the capacitor can't keep up. It's just so slow because of its time constant. Okay, so that's it for the demo there. Yeah, we won't get to the design challenge today, so we'll start next time with that design challenge. Sorry, guys. I just think we want to get through these concepts before we do that. So we have that. So that's the simplest possible filter. And if I was to make a dang it, stop. If I was to make a graph of if I were to make a graph of the amount of voltage that gets through as a function of frequency, the RC filter looks something like the blue curve. Okay. But if we have a fancier circuit, then you can get the purple curve, or you can get even steeper response functions. Okay. Those fancier circuits generally fall into a category called active filters, and they need an op-amp. We call it active because an op-amp needs power supplies. If you ever use an actual op-amp chip, you know there's power rails to that chip. So you have to give it a 5-volt source and negative 5-volt source. Whereas a capacitor is just a component. You can just put it in there. You don't need to give it a extra battery for it to work. And these active filters can get very complicated, like Chebyshev circuits and Bessel circuits and whatever other fancy nonsense. So it just becomes math at a certain point. But the crux of the design is that passive filters are simple. Active filters can do the same thing, but with a steeper response curve. And depending on the situation you have, you might really want a steep response curve. You might want all the frequencies up to 100 hertz, but then if 101 hertz gets into your system, this whole thing breaks. So you need a curve that, if this at this point right here is 100, you need a curve that goes like this and then immediately falls off really fast. Because you need a pretty intense circuit to be able to accomplish such a steep roll off in frequency. So that's something you guys can look into in your designs. We're not going to talk so much about that as a group, but that's something you can look into if you're interested. So Nathan, do you want to explain how the design stuff's gonna work?
Okay, so we'll get to this in the next class, but basically you guys are going to be split into 3 engineering companies, and you guys are going to compete against each other. So in each company, you guys have to work together to create the best design for each of these challenges. And each of the 3 companies will have one of us, like kind of like there to help you along if you need help. Within each company, there's going to be different like pods. So each pod will have like a subtask. So for example, for this one, each company has to design equalizer. So there will be 3 subtasks. So one is for designing the base filter. So like for low keys, one's going to be designing the filter for mid frequencies and one for high frequencies. So those are the 3 pods. In each of these companies, there's going to be probably around 20 people. It's based on like how many people are attending the class, and so then each pod will have around like six people. Yeah, there are these like documents. I shared them with all the people in. Like I already split you guys into your companies, and I shared the documents with you. You don't have to. I guess you don't have to work on it right now. We can work on it in the next class. But the documents are there. If you like check your Google Drive, you should be able to see them.
Yeah. So
Are we also use AI for this?
yeah, so you're free to add whatever you want before next class, or we'll work on it in a little interactive thing during next class as well. But you're free to do what you want between then. If you are having fun, don't give yourself homework. Don't do something you won't enjoy. But if you have fun with it, I'm okay with you working on it. You're free to use AI, so you can go to Claude, ask it, hey, I want a filter circuit. But what I don't want to see is you went in here and went Control-C, Control-V from what Claude gave you. I want you to give a proposal like, oh, a Chebyshev filter, blah, 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 and then link a document, like put the actual link there to a document where you in your own words explain how that filter works. So you're free to use Claude to generate ideas and like come up with things, but your actual stuff here needs to be written by you so that you're actually learning. Otherwise, you can just copy paste stuff and you're not going to get anything out of it. So you can use simulations in LT-Spice to back up your design. You can draw the actual circuit in LT-Spice. You can just draw it in a CAD just a circuit drawing tool. So you can do it however intense or however non-intense you want, but just have fun with it. Enjoy learning about filters. This is cool stuff. It's some stuff you can actually build if you were in an in-person kind of class. So enjoy the process. So the session code that we put in here, we have. That's short circuit 2 is the class attendance code. Sorry again that there was no fun activity for today. Hopefully the simulations were fun to look at. We'll have the interactive challenge for next time. So, any questions on anything from today?
Any questions? If any of you have problems using CircuitLab or LT-Spice, you can DM any of us basically. Maybe not Ishan for CircuitLab. I don't think he uses that. He's a firm LT-Spice believer.
It's true.
Yeah. But